to what you need. I'm starting the recording and sharing the screen and going to the homework. So this is the posted homework sets. Which ones do we need to look at?
Can we do 5? I don't know where you got the 1.8 times 10 to the 10 from.
The 5. Where are
I
we going
followed
here?
it mostly, and then I got lost at the end.
All right, so I might have my textbook nearby so I can look at what the question says and then go from that. What page is this one on? Do we know offhand?
230 or 330 maybe?
330, eh? Okay. 330, number 5. Let's take a peek what they tell us. That's a good idea there. All right, so 330 number 5 says two oppositely charged spheres, center to center separation of 4 centimeters. So that's there. And oppositely charged spheres. So I could have put on there, Q1 and equals negative Q2 or something like that, whatever. That they're opposite charges. I didn't list it. And says force with the size of the electric force size between them is 1.2 times 10 to the negative 9 newtons. So that's there. Did I get to the part where you're saying you didn't know where I got it from yet? I feel like maybe that was the number, but the next step here is they say that the magnitude of the charge on one sphere is twice the magnitude of the charge on the other. And so I stated that as like one of them equals 2 of the other one. So the force goes into the equation for electric force. The constant, of course, is there. This reads as essentially Q1 and Q2 here. Let me just highlight. This is basically Q1, right? It's just equivalent to 2Q2. And so there's only Q squared that's an unknown, and I just algebraically solved for Q2.
So I had like the 9.0 times 10 to the 9 2q squared over 0.04 squared. And then when I multiplied out by both, I just don't understand where you get the 1.8 times 10 to the 10 on the next line.
Oh, okay, I see. So did you, so I think that would come on my work there as the 9e to the 9 times that 0.4, just times the 2, I guess. Yeah, that's just times the 2 from the Q2Q2s.
Oh yeah, okay, I see that now.
Is that okay?
Yep.
Yeah, that's just
good.
the times 2. Yeah. And then, because I was actually just going to say that it was to do with this multiplication of the 0.04 stuff, but no, that was actually just to cancel out, of course, the 0.04, and then yeah, so this I'll go with like purple or something. This and this is this for sure. Yeah. Good. All right.
Yep. Thanks.
Yeah, no worries. What else would someone want me to go through?
If you could go back to like the first question, I just had a spot where I wasn't sure.
Sure. What are you thinking? What
On
part?
on the line where it's the KQ1 times Q2 and then over R squared times 4. Yeah, right there. How did you get from that line to the next line?
So for that one, they told me the magnitude of the force, right? So I'll just circle it here. So they told me the magnitude of the force is 3.0 times 10 to the negative 6, and that's this. And so there it is.
Okay, so it was saying like the FE is 3.0 times 10 to the negative 6, and then because you were doubling both of them, that's why it's times 4.
Yeah, exactly.
Oh,
yeah. So we had, they said we're doubling what happens if you double both the charges. So that was in here and here where we're doubling. So there they are. Yeah. And so we just basically end up with an equation where it's like the force, what it was, and then it ends up being times 4 because of the doubling effect on both of the charges. Good?
Yeah, thanks.
Yeah, no worries. So there's lots of these ones along the way. What did I have here about attractive forces when charges are opposites? But why did I feel necessary to note that? Two charged spheres. What forces result from? So I added on there the magnitudes of that. And then I put I just was talking about the signs, I guess, right? But so if we're talking about an attraction situation, then we'd have opposite charges. So we'd have a negative force, but they're listing since they said the magnet. Oh yeah, I guess because I'm sort of justifying why I have a negative in my number here, right? So basically, I feel like I'm trying to answer this question better than what they listed, right? Since they said. I forget what they said exactly, but they're attracting each other. So this indicates attraction. So I don't know why. Sometimes I don't know why they say magnitude so often, because it's something you want to actually be well aware of in terms of the sign and what it indicates and so on. So even up here, actually, I did it actually up here. Remember this here? I was just noticing here that I had justified there as well. So like the answer in the back in the side of the book or whatever is a 1.2 times 10 to the negative 5. I think the answer is better listed as a negative 1.2 times 10 to the negative 5, because then you're actually talking about the sign to do with the fact that it's attraction. Make sense?
Yeah. Thanks.
All right. Yeah, good. So all of these are very similar, right? Where there's like one of the charges, this part B one threw people for a little bit of a loop, but it's like you have to think way back to grade 9 and what would happen if an identical sphere came in and touched one of the charges. Well, they would end up sharing the charges. And so I described in an email recently to someone, this, if you had, say, originally maybe you had 4 negatives and you brought in an identical sphere and touched it. I'm drawing my mouse to go over instead of my pen here. Drawing an identical sphere comes in and touches, right? So if I bring that identical sphere in touch, what's going to happen? Well, these charges are going to spread out. These 2 charges are going to be repelled by those 2 charges. And so they're going to end up because likes repel, right? And so we're going to end up with 2 charges that are half of what they were. So if this was up here, Q, now this ends up being Q divided by 2, right? And then they talked about in the question, this new Q here. So this one's new Q. This is the new Q, right? They say they do that, and then they take this thing and they punt it into the stratosphere. It says move it off far away or whatever, right? They say get rid of it. So let me just lock this in place so I know it won't move on me, and I can then, grab the one new one, separate it out, make it, and then they just basically say move that thing off, like throw it off to the outer side. If I use my finger, actually I can do that and it goes away. Anyways, but you get the idea, right? Oops. So what did I just do? Oh yeah, so it's just back where it was. All right, so this guy moves off to far away, and you're left with this half charge business. So we've got 1 divide by 2 factor in this one. So then that's the same idea here, where this charge that they told us, right? They told us the magnitude of the charge is this, and I'm including the negative because of the attraction idea. But yeah, you get that charge, it just gets divided by 2. Then they talked about increasing the radius to 30 centimeters. So I think it's important to recognize that means that it's tripled, like the 30 divided by the original 10 is times 3. So you've got an R times 3. Notice that leads to an R, like a 3R squared, right? So if I were to show that specifically here, I'd say like 3R squared equals 3R times 3R. And so that equals, 3 squared R squared, which equals 9R, right? That's the full mathematical analysis as to why it's a factor of 9 in there rather than a 3. So let me just group that.
Wouldn't that be 9R squared though?
9r squared, yes, I forgot the square in the end there. Thank you very much. Yeah. So 9r squared, of course. And so am I missing, looks like I'm missing the square here too. I didn't even realize that before, but it's the same as it always was, of course, right? This is your force. And so I forgot it both times apparently. But so yeah, I had it in the previous line, but not anyways. But yeah, so there's your divide by 9 factor, right? And so you end up with the new force that's 9 times less than it was. So these questions, I don't like the way this textbook starts with that. But if I list the questions as do questions 2, 3, 4, and then 1, inevitably students just, I don't know why people get upset about that. They're like, why are you listing them in different order? Because I want you to do them in a different order. So I just left it, but the solution's there to help you, of course, see the idea. And what I'm talking about there is, of course, yeah, they list as positive since we're asking for magnitudes, of course. Question number 3, which one ends up being, when you get to 3 is an easier question than 1 and 2, right? Because 3 is just plug in numbers, calculate result, right? So if you go back to question 2 was about about the rate, the distance changing again, right? So the distance that between changed from 0.12 to 0.24. So we needed to recognize that that's a factor of 2 increase, and that led to the classic, r squared in the bottom. I remember the square at that time, dividing the force by 4. The weird one, if you were just looking at this and just knowing that this is double, right? This 0.24 business is double what it was. And so you're like, oh, okay, so double, so blah, blah, blah. You just do it. You skip right to essentially this step here. If you're doing that, not really thinking about this and how to get the 2, then you might hit a roadblock when you have this one, because 0.12 changes to be 0.3. It's not an obvious it's not an obvious factor number, right? So it's not enough obvious multiple more. Turns out that it's 2.5 times, but that's pretty easy to do if you're actually checking the numbers and calculating them, right? 30 divided by 12 essentially, right? So then we have the 2 factors of 2.5 less divided by 2.5 twice, basically, and so on. And then the 0.36 is back to being an easy one. It's a triple, so it's a divide by 9, So anyways, I find those questions involve more wrapping your head around it, kind of working yourself through it, versus question 3 is just plug in the numbers, right? So I'm assuming 3 is probably fine. 4, do we need to look at more, or are we good now?
I just have more of like a general question. Like sometimes I find with the questions I have a hard time figuring out where to put what stuff into the equation.
So the solution to that, of course, depending on what they are, like 1 and 2, of course, were weird, right? But you're gonna I want you to look at when you go to tackle the homework. It's not necessarily that if you've paid enough attention in the lesson and if you've read through the textbook, you're going to be able to do these questions from scratch with no problems. That's not necessarily the case in a course at this level, right? You're going to have some struggles, and that's okay, and you try and figure it out. But you want to balance, trying to figure it out yourself and look at the clock and don't let too much time go by, but try, because you build skill that way. But the step that's going to help you get that skill sometimes is certainly going to be looking at the homework solutions that I post and decipher them. That's where some work is involved, of course, right? Getting that figured out, and you learn, you're learning from that, and so you end up knowing how to do the question with some help from the solutions. And then the next time you do it, hopefully you don't need the help anymore, right? So you gradually get better and better at these skills. And this idea of like changing one of the numbers and seeing what happens to the value, that's the second time we've seen that now, right? And so that should be starting to get easier. So it's okay to have to refer to the homework solutions. It doesn't mean you're failing. It doesn't mean you're terrible. It just means that that's part of your learning process. I would recommend putting stars in your notes or something along the way. Like if you heavily needed to to refer to the solution set to figure it out, you at some point have to get to the point where you can do that yourself, right? So when we start having quizzes and tests, which I need to talk about as well, you know, you got to get to the point where you can do it on your own from start to finish on a blank piece of paper. So, you know, what do you do to do that? Well, you maybe take a solution set and you create a blank page and you read the question from the textbook again and you try it yourself. And if you can do it on this blank white page without referring to the help, then you're good to go, right? But if every time you have to refer back to your notes or to the solution set, just know that that's a spot where you'll be stuck on a quiz or a test, right? So you got to get to the point where you can do it yourself. And that just takes practice, repetition, practice, stick with it. Lots of hard work pays off. You know, that's where we're at with this stuff. Okay. So the other part, you know, I've certainly, I don't know if I said this already, Paige, but you know, like list what they gave you. Of course, the idea of given, the whole grasp concept thing, right? But for me, it's just list what you're asked for and what you're given and plug them in, like this kind of question. Certainly that helps, right? You can see exactly what you're given, you plug them in, you solve for the missing piece. This one was super straightforward because you just all the numbers plug in and you find FE, right? Sometimes you're going to have one where you're plugging in a bunch of stuff and then you're missing, you know, the part that's missing, the part that's left over, the Q2 squared in this one that we looked at. Well, that you just solve for it, right? Like, please don't think of like, oh, I need an equation for Q. You know, like just use the equation you know that has Q in it, plug stuff in, solve for Q. And that should help. So in question number 6, they told you stuff, right? They told you the magnitude of the charges. They told you they're the same. So they're both that. So I'm listing it. They told us that the force of between the magnitude of the force is 4.2 times 10 to the negative 4. So I'm listing it. And they're asking what the radius is, or the r value, the distance between, right? It's how they said it. It's not really radius, but they use r a lot because, of course, the force at any spot along a circle surrounding the point at a distance r away, you know, is going to be the force would be the same value at any spot. And that's partly part of why they talk about magnitude so much, right? Because the force would be to the left over here and to the right over there and up and down. And like there's all sorts of direction values depending on where you are around that point charge. But obviously plug numbers in. The only thing left is r squared, solve for r. Just algebra skills kicking in, that's all. Number 7 is the exact kind of thing that we did in class. I gave you different string length and a different angle and different masses and different charges, but the exact same steps carry through. So that one is already fully explained on video and whatnot. I want to just jump back to lesson 14 actually and load it up, the actual lesson, because we had a number difference. And it turns out that, to my surprise, almost, I was right in the lesson. I thought for sure I probably had made a number mistake along the way, you know, but actually the numbers, when I carried out the cosine law and calculated what the solution where I had gotten the question from, you know, should be, it wasn't 216 or whatever. After all, it was actually the number that we got in class. I'll show you what I mean. This is already posted, so you might have already seen this, but I'll just show it to you quick. Fairly quick. All right, so we had gone through and found here to the one that's hanging somewhere. There we go. So, oh, I guess it was this page here. Right, so on this page here, that can't be the one. It is the one. So it's not the hanging one that I was thinking of. Actually, it was this triangle one. Anyways, so they had said 171, but when you actually carry through the cosine law process, it actually gives 216, and then the angle ends up being 67.3. I did the solution set in full. Like here I found like, yeah, it was just kind of like there's a lot left. It didn't show where the 247 came from, and so I wouldn't find this page very easy to follow, so I redid it after the lesson, and showed everything step by step. The idea of the net force is the force of Q2 on Q1, there it is, plus the force of Q3 on Q1, and there's how to calculate the force of 2 on 1 and the force of oh, I need the distance, that's why it's not right away there. So this is the force of 3 on 1 here. So 3 on 1. I didn't list it this time, but this is the force of 3 on 1, and you can tell because, of course, the charges you're talking about are the 70 and the 55, right? So there's your two vectors. Now those are your two force values, and of course then you have to sort of think about what the directions are. And so the green there is me going back to the diagram and saying, oh, well, it's a repulsion, so it's straight up. And this one, you know, it's an attraction down to the right for now. Of course, I'm going to need more than that when I go to actually figure it out, right? So you need the angles and so on. So there's the detailed diagram there. That's the theta I decided to calculate. So that theta value, the x value is 60, and therefore theta is 30. I didn't show the idea of complementary angles, but this certainly comes from, you know, the theta plus the 60 equals 90 because of them being a 90 degree when they combine. And yeah, so I went ahead and did all the work here that we looked at in class, but it just wasn't very organized. So I did it in a more organized way. But yeah, so the x component of the red force and the y component, adding up the components, getting the totals, you know, getting the size and the angle. And this size and angle matches what you would get if you did the cosine law method. So, and sine law to get angles, right? So if you're not using sine and cos directly, like the components and SOHCAHTOA directly, then you could use cosine law if you want, and sine law. So I thought it'd be good to show you that was improved afterwards there. And something's going on with my computer, but hopefully it's fine. Yeah. So that is that. So two things I want to say maybe before I get started on electric fields and field strength and so on. I don't know. I haven't really been paying attention to the news. You know, don't really leave the house much, so I just kind of whatever, wake up, eat, go back to bed. But you know how it is. So I haven't really been paying attention to the news in terms of the dates and stuff as to whether if we're going back to school. So I was thinking we were maybe going back soon, but apparently we're not. Is that right? Is that everybody's impression that we're like online till like at least the middle of May or something? Am I right with that?
We haven't really heard anything, so I'm assuming.
I can't. I'm gonna have to plug in my speaker because I can't hear well with my. I think because my laptop's upside down in tablet mode and that I don't know where the speaker is exactly, but hard for me to hear. I'm wondering if I can get away with just yanking that thing out. Hope for the best. Anyways, and the speaker is going to go plugging in. Everybody's comments can echo around the house. Apparently, I've had complaints, but I'll try to turn it down a little bit so I can hear it, but not everybody in the whole neighborhood. So, running now? Can you hear me now?
Yeah, I can hear you.
I'll just turn that down. And on the sweet spot here. All right, so am I right? We're not back in person for a couple weeks at least. Is that correct?
I don't know.
Yeah, I
I
think
haven't heard anything, so I'm assuming we are.
I think the stay-at-home order is supposed to last until May 20th, and I assumed that included the schools, but I don't
originally
know.
we're supposed to stay at home but still go to school, so I don't know. It's so ridiculous. So it'd be nice if it was more clear. So we need to talk about you know, assessment and how that'll work and so on. So this is on video here, so it'll have to just make note that the lesson from Friday, April 30th is the one where it talks about how to get things right. So you need to go to ucdsb.elearning Ontario. That's all you really need to type in is that ucdsb.elearningontario.ca. and that's going to bring you to your e-learning homepage. If you've done online courses, that's more than familiar. Is anybody not familiar with this website? That's in attendance right now, at least. Everybody's familiar with it? Okay, so that's good. Now, I haven't done anything with this yet, so I would have to, right now, try to find this on the fly here. It means I'd have to try and find the 2021 semester and see if I can find my grade 12 physics class, but I'll certainly get that set up for you so that it's ready to go. I'm just January 2021. Anyways, the idea is you're going to be posting into a Dropbox in here so that I can have everything stay in one spot. The reason I need you to submit into this separate site is because Teams doesn't allow me to write on assignments yet. Apparently it's coming. Looks like this is probably the one. So let me just look into it here. Communication, class list. I haven't used this program in a while. But I feel like I'm getting it. Yeah, so there you guys are. So this is the right one. So let's go back to that main class page or whatever. If I go to assessments and assignments, you're going to find very soon some things in here where you'll submit. So if I made, for example, an assignment here, you'll end up seeing this when you go in. I'm going to call it quiz number 1. Quiz 1, and let's call it B equals IR and voltage current, of course. So if we were to schedule a quiz on that, that's where you would submit it. When you're submitting, you need to submit the files as a PDF. Okay, so if you're taking, I recommend doing something different. Okay, but if you're just taking pictures with your phone, and so you've got JPEGs, I can't have you submitting just JPEGs that are sideways, upside down, small. I can't write on them. Like it's just not doable for me. I'm not accepting that. So if you do just take a picture and you're going to paste the picture in to Word, right? You're gonna make it right side up. You're gonna make it the right size. Make it, what a size of page is in Word. So this helps calibrate things and get them to be usable on my end. So you would paste a picture in and make sure it's nice and big and make sure it's right side up. And then you're going to, export as, right? So you're going to save this thing and then you're going to export as, save it wherever you want, but export it as a PDF. Okay. So that's the preferred. There's one other form I can use, but I forget which one it is. Maybe I think it's certainly not JPEGs, the standard picture form. So that's possible if you're just taking JPEGs. The easier way to do this is to use either an app called Office Lens or Notes, and both of those programs allow you to take multiple pictures. And it actually kind of frames, if you put your white page on a table or whatever, and it's obvious that where the page is and there's a darker boundary around it, it'll actually put a little red box and take a picture of just the area you want, just your page. And then you can say add another picture and say there was 3 pictures to do with an assignment or whatever. You can say, create a PDF file from that directly. Okay, and it'll actually take the 3 pages, all of them right side up. You can tell when you're taking it. If you don't hold the phone at the right angle, sometimes it'll go sideways and be like, yeah, cancel that, redo it, and make sure it's right side up, right? And so you can submit PDF files. So when I'm making my solution sets like this, these solution sets that I've made here, this would be way more annoying for me to do for you guys if I didn't have the app Office Lens on my phone. I can just hold my phone above the page, not even really looking at it, to be honest. I know it's just going to automatically grab the page, like zone in or focus in on the page, and I just hit enter, or I hit take a picture right here, take a picture, and then I say add, and I do it again, and do it again, and do it again, and whatever. And all of a sudden I have like 11 pages all attached in this program, and then I just say export as PDF. Okay? And then when I get it as a PDF, I do whatever I do with it afterwards to make this, right? I print it to Smart Notebook and so on. But yeah, so that is necessary. And so that is for assessments and so on. So what I will, I guess, be doing, because we're not going to be back together shortly at least, is I'll be emailing quizzes out. So the you know what, let's just say like the one that I just made there, the power and Ohm's law, really that can happen anytime, right? So I'll just email that out and just answer the questions and take pictures, create the PDF file, and submit them into the Dropbox. So my hope is that that this is that you're doing it as a quiz, rather than just finding answers from Google or your notes or whatever all the time. But reality is I can't guarantee that for everybody, and so I'm just going to email them to students this time around. I was emailing to parents last time and asking for everybody to be supervised and so on, but I can't do that with everybody in this course, and so I'm going to treat everybody equally and just email everybody the quiz. And if your quizzes don't reflect your actual abilities on your own, it's you that's missing out in the long run. Because if we do end up coming back to school, of course, in-person tests are going to be hard if you can't actually do them from scratch yourself. Does that make sense? Okay. Integrity is a valued thing in the world, so have integrity when you're doing these assessments, I guess, is a good thing to say. Okay. Any questions about submitting? No? Okay. So yeah, let's move on. So we started yesterday whole hog into talking about electric force, right? And I did that on purpose because I want you to sort of have a feel for how you calculate things and how it looks and so on. But I want to just talk a little bit more about what the heck we're talking about. Like what is this really, right? So what is an electric field? So when you're looking at a field, I want to just describe how this is thought of, right? So the four fundamental forces in nature that you've heard of before, right? The strong force, the electromagnetic force, the weak nuclear force, and the gravity force. That's in order of strength, by the way. Strongest one is the strong, weakest one is gravity. There was a question, I guess last night, I think, where you're looking at the gravity force between objects and the electric force between objects. And the gravity force was very tiny. Where's that? Which one is that one? The gravity force was super tiny. And they asked you to, I forget which one it is now. There it is. So half a kilometer apart, 10 kilograms, and so on. So the value for the gravity force between them was like 2.7 times 10 to the negative 14, 0.0000000. I lost my breath trying to say enough zeros, versus 36,000 newtons. I think that number's not quite what I was, anyways. But yeah, so we have, oh yeah, why do I have 500? But that's of course because it's meters, right, and so on. But yeah, so these numbers, like, look at the difference between these, the electric force between them and the the gravity force between them, and that speaks to two things. One, the gravity force is very, very small, right? But it also kind of indicates, like 1 coulomb of charge is actually quite a lot, whereas 10 kilograms isn't a lot, right? But 10 kilograms is a fair bit of mass, and 1 coulomb of charge. I just when you charge up a balloon by rubbing your head, how many coulombs are you really contributing to that thing? The answer is definitely not 1 coulomb. Like, it would cause major forces if it was. As soon as you rub it against your head, it would, like, go flying towards a wall and smash through the wall. And if there was that much force, right, or that much charge. So they ask you to, like, calculate everything, and I just left it as, like, the electric force is huge, the gravity force is a tiny little speck. So not drawn quite to scale. I wanted to be able to show the gravity force a little bit. But basically, it's pretty clear the gravity force is way smaller. And so when they're asking to determine the net force, you're really just talking about the electric force, right? So you calculate acceleration based on
on the electric force. And then they say to do that again without gravity, and be like, wow, I already did, because gravity is 0 decimal zeros, you know, in comparison. Anyways, so that relates to this here a little bit, anyways, in terms of the strength. So that should be familiar. Next step here, we're talking about field theory. So field theory was first developed to help scientists just be able to understand what's going on, right? Because they see objects that are transmitting a force, causing a force on other objects, but there's no strings attached, right? There's no, nothing, no contact between them. So you actually refer to them as non-contact forces sometimes too. But action at a distance force, non-contact force, all mean the same thing. So field theory, just to summarize what I just said, is the theory that explains force interactions or attractions and repulsions between objects in terms of fields. So I feel like maybe this could be in quotations here, in terms of fields, right? A field of force, or in other words, like force field, right, exists in a region of space when an appropriate object placed at any point in that field experiences a force. What do they mean by appropriate object? Well, we're talking about a charged object if we're talking about an electric field, or so let me just talk about a charged object, like a charge. If we're talking about electric field, we're talking about a mass. If we're talking about a gravitational field, etc. Right. So here, appropriate object. Let's jot in there, i.e., a charged object with electric fields. So that's what they mean by appropriate object. So when you visualize this, science fiction, of course, talks about force fields of force. So these people were on like an alien planet, and they had a force field around them, or there's the Enterprise with the force field around it to like protect against enemies. It seems kind of like science fiction. Well, it is science fiction, obviously, but force fields are actually kind of a real thing, right? Earth is protected by a field of force around it. The magnetic and electric field around Earth protects us from high energy electrons and radiation that comes from the sun. If we didn't have a strong electric and magnetic field around Earth, yeah, we'd get bombarded by radiation a heck of a lot more than we already are. And it's quite possible life might not have even been able to exist on Earth if we didn't have strong magnetic and electric fields. The Earth's rotation is necessary for this to exist. And so the fact that the Earth is rotating makes the fields possible, which makes life possible. The Earth is slowing down. The gravitational attractions between the moon and the Earth are gradually slowing the Earth down. So in like 18 million years or something like that, the Earth will have stopped rotating, in which case we'll end up not having protection from radiation, which is scary to think of, except when you realize that we're talking about 18 million years from now. So here's a nice picture that shows the actual idea of like so here's a charged particle coming from the sun, and it's like, ooh, it gets repelled away by the fields around Earth. Okay, so we're going to see more diagrams like this in terms of like, these are like electric field lines, and they show like what force or what path that a particle will travel because of the forces. So you picture like little arrows along here all the way. So a particle right there would have an arrow pointed like this, meaning it's accelerating off to the side, accelerating off to the side, accelerating off to the side. So it actually deflects the particles that are coming from the sun and makes them not even hit the Earth. Now, of course, some do hit the Earth, but not nearly as many as if we didn't have fields. All right, questions so far? We're good? Just trying to help you visualize what the heck we're talking about, right? So just to make things seem simpler, we're going to start with just the super familiar gravitational field. And if I ask someone to put arrows in here that indicate what direction a force would be, you'd be like, well, of course the force is going to be in, and it's going to be in all over the place, right? So we have tons, however many arrows you wanted to make, along the way. So just picture if I kept going with this, I'd have 100 arrows all pointing towards the center at various angles, right? So all over the place we'd have, just to speed this process up, of course, we'd have, you know, like this all over the place, right? So the existence of a gravitational field is actually, you know, observed or shown by the fact that the force exists. So you put a mass here, right? Put a mass at any spot along the way here, and it experiences a gravitational force of attraction. That shows, or that is, you know, shows that there's a gravitational field. Okay. I'm not going to spend any time on this page at all here, but gravitational fields, Einstein, you might remember from grade 11, you know, Einstein actually sort of realized that it's actually caused by the warping of space-time and so on. But you picture like the moon sort of rolling around in this like funnel kind of shape, right? And so if you're interested, this video talks about the truth about gravity, how gravity is not actually a force. It just seems like a force from our observations. Grade 11s saw the video already. Grade 12s, I'd suggest maybe watching that for sure. And it will probably cause your head to explode, and we'll probably have a little video session at some point to help you understand what the heck it said. But it talks about sort of the Einstein's explanation of gravity, of the gravity field. Anyways, it's not really related directly to what we're talking about. So what we are talking about now is, of course, electric fields, right? So same idea as the gravity one. If I had a positive charge near a negative charge, then we would have electric force of attraction, right? Electric forces of attraction causing all of these things. So just like the other page, I'll show a bunch, but then cut this down a little bit where it's like we'd have a positive charge attracting all the time, right? So instead of mass, we're talking about charge. Whatever, right? So that's very similar to gravity, and that's why I'm showing gravity, which we feel like we understand great, and then it's like, oh, so charges are kind of similar, right? The difference is that if we had a positive charge, what would happen there? Well, of course, there'd be a repulsion. We know that likes repel, right? So jot that down, whatever, but that likes repel. And so the electric field around a positive charge, and remember we're using this idea of a positive test charge, the conventional unit or idea in electricity in general is like a positive test charge. So positive test charges would be repelling from this. And so that's new for what we're doing now. Okay. So similar to kind of explaining what's really going on with gravity, when we explain what's really going on with electric fields, we actually have to talk about magnetic fields at the same time, and we'll deal with magnetic fields more later on. But it turns out that electric effects and magnetic effects are part of the same thing. They're part of the electromagnetic field. And so there's an electric field part and there's a magnetic field part. You cannot have one without the other. They actually coexist. So an electromagnetic field always surrounds charges. Okay. So, and the disturbance, so when an electric charge moves or changes, it sends out vibrations in this electromagnetic field, which always surrounds charges, and it sends out this disturbance called an electromagnetic wave, which you're familiar with electromagnetic waves. You might just not kind of connect the dots and realize it, but we're talking about like light and radio waves and so on, right? The speed of an electromagnetic wave is the speed of light. So we're talking about light, we're talking about radio waves, we're talking about microwaves, right? We're talking about all of those parts of the electromagnetic spectrum that we've looked at previously in grade 10 science, I guess, primarily. So the way that looks, remember I said there's two parts. There's an electric field part and there's a magnetic field part. They are at 90 degrees to each other, okay? So they are at 90 degrees to each other. So you have the electric field part going up and down, you know, as a picture an electron. Picture an electron actually physically getting moved up and down, like vibrating up and down. Okay, that's going to make the electric field part pretty obvious, right? And there used to be a nice little applet that doesn't work anymore, where you had an electron here, and then there's an electron here, and then there was another electron here, and you could grab this one and move it up, and then this would be, I suppose, a positive charge here, positive test charge. If you move this one up to here, then this one gets attracted and moves up to there. And then if you move it down to here, this one moves down to there, and you can sort of picture like how they're attracting each other, right? So they affect each other. And then if you bring it down and let go, it actually goes and bobbles back and forth. So then this one bobbles back and forth too. And so you can picture how an electromagnetic wave propagates or moves through space because of that idea of the one affects the other, right? One charge affects the other. So the weird part that we aren't talking about much more until later on in the course, but as the electric field fluctuates up and down, at the same time as that, the magnetic field, there's a change in the magnetic field as well. Okay, so it's perpendicular to it. So when this happens, right, this electron moving up and down causes the electric field, right? I should have used different colors because, well, the purple, that's almost purple. So anyways, should have used orange for the electron, but anyways, that causes the electric field. That's the unknown part. But then as a result, there's also a magnetic field that's perpendicular to it. And that is what an electromagnetic wave really is. And it turns out the speed of that wave is 3.0 times 10 to the 8 meters per second, or 300 million. So there's just another diagram of it. You know, you can sort of two-dimensionally represent this 3D idea of a sheet of plywood that's vertical and a sheet of plywood that's horizontal. And you got they're showing the magnetic field vertically this time, and the electric field horizontal. It doesn't matter which is which, of course. You can view it from any angle. So the wave is going through much like this. You can see it across the page, if you will, right? So if you're drawing this yourself, you know, you maybe draw like a parallelogram representing the flat sheet of plywood, draw a line in there, draw a parallelogram this way representing the vertical, draw a line in there, and then, you know, both of them together shows you the weird kind of combination of both of them. Okay, so that's an electromagnetic wave. Questions? Okay. So gravitational fields, when people sort of learn to talk about this and they're like, oh, okay, this makes sense. They calculated a whole bunch of things. A guy named James Clerk Maxwell developed what are called Maxwell's equations for electromagnetic waves. They're awesome. They work amazing. They're not very fun to use because they're so complicated, but they're very, very, very good. They predict things with extreme accuracy, right? And it's all seems very well understood. This kind of thing it occurs with gravity as well. If a planet, you know, a large mass was moved up, then a planet or an object nearby that's attracted to it would move up as well, just like in the electric, you know, positive and negative charge idea when you have attraction. So it's you know, basically a long time ago, people said, oh, there should be gravity waves, right? And so this is what I wrote, you know, originally I put last time I taught the lesson, but now it's like, you know, 12 years ago now or something, or 20 years ago, whatever, right? 18 years ago or so, maybe, from the first time I taught grade 12 physics. So I had written, this should exist. Scientists, you know that gravity waves should exist, but they haven't been observed so far. And so ... it was like, you know, if you want a PhD in physics, go looking for gravity waves. Well, then what happened in the years since that? Well, scientists, of course, actually discovered gravity waves. So they built a detector to detect gravity waves. And that article, you know, was the heading from it. How that detector works is they have a super long, I think it's like 4 kilometer shaft in the ground this way. And then they have a 4 kilometer shaft in the ground this way. To expand my page a little bit. And they are super straight and they are super well controlled and so on, and they're at 90 degrees to each other. And they take a laser light and they actually send it through what's called a beam splitter. I actually have one of those in the 124. but they send in a laser there, and it splits in the beam, and one beam goes this way and bounces back off of a mirror, and one goes this way and bounces off a mirror. And so they're supposed to be both 4 kilometers. They're not quite drawn to scale here, right? And what happens is, if there's a gravity wave, so let's picture a gravity wave like this. Okay, I should point out that these 2 rays, one, it's something we'll talk about later in this course, is that the light, when it comes back, interferes. And so there's actually what's called an interference pattern. That exists there. It's very similar actually to when we looked in the sound unit. We looked for areas of destructive interference and nodes and antinodes and so on. It's actually the same as that, only with electromagnetic waves. So there's going to be a very, very, very predictable interference pattern, you know, whatever the pattern would be, right, of nodes and antinodes. Picture them, right, in this you know, detector here. What happens when a gravity wave comes along is the gravity wave actually shrinks and changes the dimensions, the space dimensions. So if this is my when the gravity wave comes along, it actually, what can I do here? I guess I'm going to shrink it that way. It would change the length of that shaft a little bit. Okay, and what that does is the gravity wave changes the length of one of the shafts. Which changes the interference pattern. So if they see an interference pattern change, and the only explanation could be that the length is changed, but they know, of course, that it's still the same, you know, 4-kilometer shaft and so on. This change here in the length is because of the gravity wave. Okay, so this is like delta D due to the gravity wave, and so that changes the interference pattern. You get a new pattern that, I don't know, shifts to the left or whatever, just changes, right? And they can calculate that change, and based on that change, they can calculate, you know, where the gravity wave came from, what happened, like 2 black holes collided or whatever. Okay, so there's a chance in the future that you're going to have big arrays of these things, and they'll actually use, they'll be like gravity telescopes. You can actually observe what's going on in outer space by analyzing gravity waves. Pretty fantastic stuff. If you want to search more about this, search LIGO, LIGO, and it's the gravity wave detector. Pretty cool stuff. Not too shabby of a way to get a PhD. Questions? All right. Next step, let's just talk a little bit about fields. When you talk about fields, the math actually involves exchange particles. So in the strong nuclear force, I mentioned this in chemistry unit in grade 9 and 10, that the strong nuclear force, the objects are held together by the strong nuclear force, which is called the gluons. So in chemistry, I wish chemistry teachers would say, hey, we've got our protons and our neutrons here. Yeah, that makes sense. And so then our electron is negative, and so it's attracted, and so it orbits around, and because opposites attract, you know. But then I wish more students would ask it. I wish more chemistry teachers would talk about it. But it's a little bit of physics involved. It's important here is that why don't those protons repel apart when you have, you know, 6 protons in here and 6 electrons, of course, around. You know, why don't those 6 protons repel? And it's because they're held together by the strong nuclear force. So what's happening is those protons are constantly exchanging what are called gluons back and forth. Gluons are the specific kind of exchange particle to do with the strong nuclear force, because they name that in a not so creative way because they glue protons together. So they call them the gluons. Kind of cute. They are part of a classification of a particle. I have to remember years going back, but I believe they're called baryons, or no. I'll come back to it. Anyways, there's a classification of particles. They're bosons. Here it is, actually, down here, bosons. They're bosons. So bosons are exchange particles. So with gravity, you can picture these gluons. With gravity, they picture that there's a graviton, and there's a PhD waiting for someone there that can actually detect gravitons, because they've tried and they haven't managed to yet. With the weak nuclear force, there's the W and Z bosons, very well understood. All the equations to do with it, they've been discovered. They have all sorts of interactions in particle accelerators where, like, okay, this particle changed to this type, and as it did, it gave off a W boson, and everything's really well understood. It's called the Standard Model of Physics. Okay, with electromagnetism, what we're talking about here, with electromagnetism, this seems weird to understand or weird to imagine, but with electromagnetism, the exchange particles are photons. So when you have a magnet stuck to a fridge, the magnet's actually exchanging photons in some weird way. And the weird way is Maxwell's equations. Maxwell's equation describes electromagnetism extremely well. Is what it is, right? But these exchange particles ideas is what drives the. So there is actually an interaction between these objects that aren't touching, and it's these exchange particles that are passing back and forth. Weird, wild stuff. Questions?
I feel like the different names, like the gluons and stuff, like when do they kind of use them? Like in what context do they come up?
Yeah, so if I were to show, let's go, trying to remember, let's say proton decay diagram, what they're called. Another name for them, but so this is what it looks like. And so basically here we've got like a proton that's decaying. Actually, they've got, yeah, so they've got an up quark. That's not what I'm looking for. There we go. This is a proton. So we got two up quarks and a down quark, and it's decaying to become an electron and a down quark, and then it gives off a pi meson, and it's basically this is one of the particles to do with the interaction. And so there's the X boson that's interacting between, that's where it happens. That's where they talk about it in the context of talking about particle interactions. Does that make sense?
A little bit more, yeah.
Yeah. Well, it doesn't make sense yet, but at least you can see, okay, this is actually the standard model, a physicist talking about quantum. This is nuclear physics is what this is, right? So this is a nuclear particle, a proton that's decaying into an electron and so on. Let's go with neutron decay, because this is the one that is related to isotopes, which you're familiar with. This is neutron decay diagram. So if you have a neutron is decay of a neutron, let's go with this one. So you have a neutron decays to be a proton, an electron, and a neutrino, right? And then there's a W boson that's interacting between these, and that's like that's the weak nuclear force interaction between these particles. Okay, so we've got these exchange particles that are shown with dotted lines between things during interactions. So there's a neutron decaying to be a proton. It also gives off, as it does that, an electron and a neutrino and so on. So this is what happens when radioactive decay happens. If you have a particle, if you have an atom, that has like a couple, too many extra neutrons, right? The neutrons are there to help hold it together. But if there's a few too many, neutrons on their own do this. They're not stable, right? So neutrons that are on their own aren't stable, and so they decay, and that's why certain isotopes aren't stable. They're radioactive, right? So that's related to that. But then there's your exchange particle here, right? That's the W boson, right? Exchange particle to do with the interaction, to do with the weak nuclear force. So that's the weak force interaction. And I'm only showing you this out of interest, and so later on you see it, hopefully things piece together, but it's certainly not required as part of this course. I'm not going to ask you to draw like the diagram of a neutron decay or anything like that. Okay, that's a good question. All right, so Electric field lines. So an electric field, of course, is a region around a charge that in which there would be an electric force on other charges, right? So if you have a charge, then around it, there's going to be forces on other charges. So I don't think we need to do this part. This was a recap of things here. So it was like, remember we talked about, we're describing action at a distance, non-contact forces. We describe it by saying there's fields. I just basically put on this page here. I just left the page in because I thought it was a good summary. But basically here, when we're talking about the appropriate particles, for gravity, it makes total sense to say when a mass is in the presence of another mass, another mass's gravitational field, there's a gravity force on it. So now we're saying, well, when a charge is in the presence of another charge's electromagnetic field, there's an electric force on it, right? So it just shows the equivalence between the two ideas we're talking about. And I do want to point out that I am hoping to help this new one become familiar by describing the other one that we feel familiar with. But in reality, they're both fields. They're both weird, right? But for some reason, people ask, how can a magnet attract another magnet without touching it? But no one tends to ask, how can the Earth attract mass without touching it? And they're the same thing. They're both just as mysterious. It's just that we lived with gravity so much. Of course, it seems familiar to us. Okay. So anyways, that was just a little recap of what we had done. I want to focus on electric field lines. So electric field lines, a lot of words here, but they show what direction the force would be, right? So if we put a positive test charge somewhere, so this is a big positive charge here causing an electric field. And then this is the little positive test charge. So this guy here is the little positive test charge, and it's going to have an electric force, Fe, on it that's to the right. It's going to repel. And so field lines are shown to show what direction, certainly at least what direction a positive test charge would go if it was in that electric field. Okay, so that's the starting point of showing field lines. So if, this does say here, if we had negative charges, if we had a negative charge, then a positive test charge, of course, would have a field that goes in, right? So the field would be like this, whatever, right? So that's for this one. It's just the direction a positive test charge would go, right? So there's a positive charge, yeah. So force is felt by a positive test charge. It's important to remember that weirdness. So the diagram to the right, for example, it says here a stationary charge would move away and a negative would go towards and so on. Note a test charge is a particle with a charge so small. Let's make note of this part here. A test charge is a particle. It's so small that this charge here isn't actually making much of an electric field. It's a relative size thing, right? We're talking about, billions. Let's picture it in money. This is billions of dollars and this is a nickel. If a billionaire picks up a nickel, they're not more wealthy in real terms, right? So this is like a huge electric field. This one's a very minuscule electric field. So we're only talking about the field due to this charge. We're not talking about the field due to the little one because it's inconsequential in comparison. So that's important to recognize because you're going to have equations where there's two Q's and one of them's the one that's causing the field and the other one's just the one that's like, being affected by the field. Okay. So you got to watch for that. Can be a point of confusion. So down here, I'm saying note that this is actually a three-dimensional field, but it's hard to draw the 3D, right? But there would be a line coming out straight towards you from here, and there'd be a line going straight back, and there'd be a line, like it's very three-dimensional thing, right? So like in 3D, you could picture more lines, but it becomes very hard to understand or hard to visualize. Also, what do we have? Electric field lines represent the net electric force per unit charge. So field lines indicate what force there is, as I said already. If you're talking about this is an important line I highlighted and underlined here. Okay, so they're talking about the net electric force per unit charge. And so, at a particular position, they have this net force. So at this spot right here,
this is Fnet, right? That line indicates the net force. So it's impossible to have two electric field lines cross each other because you can't have two net forces, right? Net force means the result if you add up all your forces. So if you add up all your forces, you can't get two different results. It actually relates to grade 11 with the idea of whether something's a function or not, right? If something's a function and it can only give one result, so you could actually use this as an example in grade 11 if it was understood at that point. But yeah, so you can't have two net forces. You can't have two results if you're adding up all your forces. So this is an important statement here, that field lines never cross. Okay, because if they did, that would mean there'd be two net forces, which just doesn't make any sense. I'm trusting you will key your mic and ask a question if you need. Okay. Furthermore, the denser, I don't know if that's a correct word or not, but the denser or more concentrated the field lines indicates a stronger field. Okay. So basically here, if I draw a circle this size, I'm managing to touch two field lines. But out here, that circle only manages to touch one. So you can tell that this field, the field strength out farther is less, right? So this one has two lines. Out here only has one line. And so you can tell the field strength is tapering off. It's reducing as we go farther away. This one's only one line, so it's weaker. Denser and weaker, and anyways, yeah, all good words, sort of, right? But gets the point across. So yeah, it's just describing what I just looked at there. They just did the reverse, saying it's more concentrated in the middle, so it's stronger. So more lines means stronger in there. You'll sometimes have situations where there's two electric fields overlapping, like more than one charge near each other. And so the fields combine to give like the net effect. And so to determine the net electric field, you'd use vector addition. So, roughly speaking here, if I had a positive charge and I had a negative charge somewhere along the way, maybe at this spot right here, you can picture there would be, actually, let's move it a little closer. So that right there. So you could picture that there would be a big repulsion force from this one. Let's do this, right? There's going to be a big repulsion force like that, Fe, there. And then from the red one, there's only going to be a little bit of an attraction force because it's further away, right? And so then, the result of these, you would actually add up vectorially. F net would equal, Fe plus Fe if I use the color coding, but basically, the Fe from the positive one and the Fe from the negative one. They actually add up vectorially. So that's very true, but hard to do because you're talking about like everywhere, right? We're talking about the electric field everywhere from everything, and so on. Let me just grab this picture. I want to make that picture, show that picture here as well. So these are field lines between a charge that has charge of 4Q, like 4 times as much as the other one essentially, right? And so what's happening there is you can picture a positive charge. Wherever I put a positive charge, which way would it go? Here it's getting repelled by the positive one and attracted by the negative one. So it's clearly just going to go like sideways. There should be a line like straight over as well in the middle. But here you can picture it getting repelled for a while, but now it's far away from the positive charge. So it's going to start getting attracted to the negative one, right? So you can picture all of these lines being like the path a charge would take. If a charge was here, it would follow this path, right? If a charge is here, it'd follow that path. If a charge is out here, it actually just goes off to infinity. If a charge is here, it just goes off to infinity, and so on. That's what this is saying. Okay, that's one of the things that this diagram is showing is directions, a positive charge would go. So I'm going to show you a little bit more about this diagram because it's the way the textbook showed it is not quite good enough.
So field line and density doesn't always indicate field strength. Okay, so make a note of that. Field line density doesn't always indicate field strength. So the top one of the lines in 340. This textbook is good in a lot of ways that you're using here. It's good in a lot of ways, but they sometimes just don't explain things, and it's bad in that way. So it's good in the explanations it does give. So this one, they have this line. It says when charges aren't equal, the line density is not an accurate representation of the relative field strength. And I'm pointing out that that's due to the field lines starting and terminating locally. So if I show you more detail here, this paragraph here, I'm going to show you the idea of this paragraph and talk about it. But they're saying you've got a 4Q and a 1Q, right? So one's 4 times as big as the other. And it says the number of field lines, right here, it says the number of field lines leaving a positive charge or approaching a negative charge is proportional to the magnitude of the charge. So they're saying the number of field lines from this one is proportional to the, to the number of field lines here, and the proportion's the same as the 4-to-1 ratio. Okay, but is that obvious in this diagram? No, it's not obvious in this diagram, but I was so happy when I managed to make sense of it. So this little down here, it looks like a scary insect. See it? What I did was I drew lines from the 4Q, roughly evenly about a 360-degree thing. And I actually drew 16 of them. So notice this one goes off to infinity. So this one goes off to infinity. This one goes off to infinity. This one goes off to infinity. All of these go off to infinity, right? It's not until we get in this small angle portion here where we get one that actually goes and terminates here and actually goes and terminates there. So you picture out of the 16, only 4 are going to the 1Q, to the 1. And so these are in a 4-to-1 ratio, like 16 to 4 is the same as 4-to-1, right? So like that to me deserves some exclamation points. Like it actually shows this cool insect looking thing actually shows the what they're saying here in this paragraph. And that's what I mean by this textbook is good in some ways, but in some other ways it's kind of rough, because this paragraph, you'd have to read that like I did 7 times before you're like, oh, okay, because you're looking at the picture and it doesn't really go along with what they're saying, right? It doesn't emphasize what they're saying. And so that's my job right now, is to try to emphasize those things and help you understand it. So the number of field lines is proportional to the magnitude of the charge. So there are more field lines around the Q than whatever. That would be much easier to see if there was an obvious 4-to-1 ratio. And that's what I managed to accomplish with the very cool looking insect diagram. I was very pleased with this slide. Yeah. So another interesting thing they say in this paragraph that's not obvious is that somewhere here, where does it say? Far from, very inconspicuous little line. That's what drives me crazy about this textbook. Far from both charges, the field represents the charge, single charge of a magnitude of 3. So they have another diagram on the next page that looks like this. And they don't have this extra wording, of course, right? It's very inconspicuous. They just have this diagram there, and no one even knows why if you're not paying attention. But basically, this shows that this overall charge, so in this region around here, right, in that region around there, that's essentially the field lines of a 3Q. I guess it was negative, but whatever, negative or positive. So that's field lines of a 3Q, just would determine the direction. So if you extended, and if you zoomed out even farther and extended these lines out, whatever, the density of these lines is going to be the same as like a 3Q density. Right? You'd swear there's a point charge in the middle here that's a 3Q. Okay? So I'm going to be able to show you that in a second, more in a different way as well. But so 2 key things from this, right? If you look at the number of field lines here, the idea of the field strength being represented by field lines gets messed up by the fact that some of these lines could, like, it's super dense here, but it's because they're going back to the charge is the best way I can describe it right now. So just be careful with field line density indicating field strength. It's not quite cut and dry. So we live in the future, my future at least anyways, right? So when I was in high school, we didn't have ways to demonstrate or show these things. So for example, here I can just show, make this be 0. There we go. So right now, this is just showing the field around a 2Q charge, right? There's a 1Q. Notice how there's less lines. A 2Q, there's twice as many lines. A 3, a 4, and so on, right? So the nice thing about this is you can actually see what it looks like if there are opposite charges nearby each other. So let's put a 2 and a 2, right? So this is what there's opposite charges near each other, and it would generally look like, trying to get it to be the nice looking version. Here we go, like that. Generally, you show lines coming out from each one, but of course these lines can't cross, right? And so they kind of push against each other. They end up like, you know, repelling off of each other, and because they can't cross, and that actually helps you visualize why there's a repulsion here between two like charges of 2, +2. Okay, so that's the common like repulsion diagram. And then if we had opposite charges, you can see that, you know, an opposite charge going from here is going to be like, oh, I'm going to get attracted to this negative one once I get closer, like I showed you on the other diagram. Okay, so this helps show fields in real time and so on, which is pretty cool. So that's good. So then that relates to this. I put, this is a screenshot of a 4. So just the red one has a 4 charge. And then I've got here just a 3. So picture like in this region out here, picture in this region like the line density, right? Oops, didn't allow me to do a curve that time. But anyways, the line density there and there. And then picture the line density here. You can tell that this one, just grab pen types, pen blue. You can tell that this one and this one are the same as each other, right? Well, this one's created here. This one's created by having a single 3 charge. This one's created by having a 4 near a -1. And so basically math works. It's like 4 plus -1. I'm just going to do this here. 4 plus -1 equals 3. You know, that seems to make sense, doesn't it? But honestly, good luck. Good luck getting this in this interpretation down pat by reading those textbook pages. Oh my God, like I can't imagine trying to do this. Now, I'm going to say something funny, but I can't imagine doing this as an online course. What I mean is an online course where you're looking at pages, not hearing anybody explain anything, and you're looking at digital pages and you're looking at textbook pages. The digital pages tend to be the same as the textbook pages, so it would be rough. So I'm glad I'm at least on real airtime here to help explain this. That you know, helps a lot. And I've heard lately the idea of like, oh, it's hard to do this online. And yeah, absolutely it is, right? But keep in mind, the more you work at this, the easier it's going to be. You've got those solution sets. You've got me to explain. You've got, you know, this is almost as good as doing it in the building. Almost, not quite, of course, but from my point of view, I'm delivering almost the same product. So I hope that helps you, motivate you to say, you know what, I can do this. I just need to sit down at the kitchen table, have the solution sets available, try the questions, learn from it. You know, like that's the point where we're at. I gotta try and motivate people to do that. So this is just a bunch of screenshots of the old version of it. So there's like a large charge and a small charge. We already saw that. So of course we've got the idea that a large charge has a higher concentration of field lines. Just showing here, this is the repulsion case. And so again, the idea of when you draw this, you would draw like a line, you know, maybe draw like, you would draw this line coming out and you draw this line coming out, but they can't like just butt heads, right? So they have to like repel off away from each other, right? And so the idea of there being like a repulsion here away from each other because they can't cross. Because you can't have 2 net forces. It's kind of a weird way of describing it, but so there's another version of that. And then I've showed the light charges one, so that's the same as that. And then this is light charges when there's less lines. You know, it's all good.
So this is the large versus small when you have opposite charges. And I can just do that real time here instead. It's nicer. So if I crank up one of these to be way bigger, then oops, I want opposite charges, right? You kind of see like the idea in that original picture that this one here, right? The red, which one's which there? This one's the blue one, right? Yeah. So there's tons of field lines around the blue one, and it's kind of overpowering that one. If you looked from far enough away, this would eventually start to look like just a -3 overall charge. We don't have, unfortunately, the ability in this applet here to zoom out as much as I'd like to show that. So, kind of neat, right? Be able to see these, and to be honest, it may be hard for you to appreciate because you've grown up in this time frame and so on. But man, it's nice to be able to visualize these things, right? But boy, it's sure nice to be able to picture like the complicated field lines from a complicated set of charges, and it just like magically appears on the screen. And so it's like this didn't exist when I was your age, when I walked uphill both ways and all that good stuff. But it's certainly pretty nice to be able to see. So there's other applets. There are links to other applets as well. So we're getting the idea of like what fields look like between charges. Okay, getting a little visceral sort of feel and understanding for what the pattern of the electric field, shape of the electric field is. Questions so far? Okay. So one other neat one to show you, and I'm deliberately actually showing you parts of this chapter. So if you do read through it, like I said, it's rough, but try it. But if you do read through it, there's more than one version of this right here. And so I'm going to show you a field that shows up between parallel plates that have a charge on them. Okay. So this is parallel plates that have a charge built up on them. There isn't a battery connected. Okay, a battery was connected originally maybe to charge it up, but now you've removed the battery, and now these things just have a charge on them. Okay, and so there are it's a neat case. Parallel plates are often used. They're used in old school TVs, like the old tube TVs where they have like two parallel plates, and what they do is they cause the electrons that are given off by the hot metal in the back of them. It's called a thermionic emitter, but an electron would repel from that. And then there's a little hole here, and then the electrons shoot out towards the front of your TV. That's how TVs, the old school TVs worked, the ones that are big and bulky and heavy. Most people have the flat screens now, of course, LED and plasma and whatever, right? But anyways, so in a parallel plate, there's some neat things, okay? Notice how the lines are drawn, how it's like very uniform. The electric field between a parallel plate is uniform. Okay, so it doesn't matter where this electron is, if it's close here, close there, over here, over there, or this positive, if I can move it around, it's going to be the same force on it, which is really neat. And it allows for some pretty easy calculations later on to do with it. Okay, so it's uniform. Yeah, basically I need to say along the way here, by the way, the area, I'm going to just reveal this right away here. The area between the plates needs to be large in comparison to the distance between them. Okay, so that I'll even just copy and paste this one up here again, because I feel like this statement about the charge is uniform everywhere is a little bit overstated, because in reality the plates have to be pretty big, and they have to have a pretty small separation. But as long as you have those things, then in this region in the middle here, not near the edges, right? Not so much near the edges, you have a nice uniform electric field. The size of the electric field between the plates is proportional to the amount of charge. So the more charge there is, the more force there is. That makes sense. That's not surprising, right? Aside from the bulging at the ends, of course, the parallel plates, outside of the plates is zero. So aside from a little bit of a bulge there, we've got zero electric field outside.
So you can be fairly close to a parallel plate, and there's a huge, maybe a huge electric field inside between the plates, but right nearby there'd be nothing. So what does that mean? Like if I put an electron here, it accelerates like crazy towards sorry, I had the arrow going the wrong way. Why didn't someone tell me that? I'm just looking at what I had there. Oopsie. So I need to grab those two things. Upside down, of course, electrons repel, right? So they have, what do they have? So I got tricked by their original, where I got this from here. That would be going the other way. Why do they have that? Oh my gosh. All right. I don't know how I didn't notice that until now. No, this would be repelling, of course, right? Wow. So because the positive was going that way, I automatically just made the negative go the other way. Anyways, so outside here, so this relates to the idea of a definition of a field, right? If I put the charge here, it experiences a force. If I put the charge here, what does it experience? Now, does it experience a force? I put it out there. The answer is no, right? So 0 electric field, no force. Okay, that goes along with the idea of like what a field is. You know there's a field if there's a force on an appropriate object. That's a quick little review. So weird thing that's true about this, as long as you don't go too far apart, right? As long as the distance between them is small in comparison to the surface area, you can vary the distance between these and it doesn't change the electric field strength. Okay, you can make them twice as far apart, you can make them twice as close together. It does not change the strength of the electric field at all, which is weird. Okay, and tomorrow you're going to see, probably tomorrow, no, well, Monday, but yeah, you're going to see what seems like a contradiction to this. Okay, so just to warn you, it seems like a contradiction to this, but in this case, when you've got a charge built up, voltage is no longer connected, right? If you double the distance, the electric field strength stays the same. And this bothered me for a long time. It always bothered me, especially because there's a contradictory statement that you'll see on Monday. Okay, but the way you can make sense of this, I finally figured it out after, because people don't tend to explain things that it's enough for me. I don't know, like it's just it kind of gets glossed over and everybody's like happy to move on as long as they get the marks, right? But if you think of this situation, it takes a lot of work to increase the separation between these plates because they're attracted together really, really strongly. So if you force them apart, you're actually doing work on that system, right? And so that increases the potential energy between the plates. And that's how the electric field intensity remains constant. Okay, so let's think about it. If this electron is repelling from here all the way up to here, right? Then that's like a force on it over a distance. And now if I make that force go over twice the distance, obviously the electron's going to get twice the energy. It's getting a push for twice as far. So it's going to have twice as much energy. But that goes along with what I said here. We're increasing the distance, that requires more work. So there's more potential energy between the plates. So it all makes sense. Right? Even though that seems odd. You can't extend this to infinity though. Like if these plates are super far apart, the field lines start going other places basically instead of to each other, right? So this distance still has to be small in comparison to the plates always, but it can be twice the size of the other small distance and still be within the range of numbers that make sense. This is an important slide to just try to, kind of get your head around for now, because then when we see the other version, we can compare them. Okay, but I'm not doing the other version today like the textbook does because I want to be able to compare them and give you some time in between. So electric field lines point away from positive charges towards it's the direction a positive test charge goes. Just a little summary here. Direction. Test charge. Also here. Test charge would go. So all of the stuff I've been doing is just very qualitative, I guess you'd call it, right? It's ideas and concepts. The next step is going to be to put some numbers to it. But for now, the summary of the ideas that should make sense at this point is that, the electric field lines go away from positives towards negatives. It's the direction a positive test charge would go. Test charges have small amounts of charge, and so their own fields, they don't really create their own field. Electric field lines never cross because you can't have two net forces, right? So, and one net force doesn't make sense. And the field lines represent net force. What else here? The closer the field lines, the stronger the field, generally speaking, except when you have multiple charges and you have charged field lines terminating and so on. So this is generally true, I'm going to say. But with multiple charges for that, right? More of a reminder at this point that you got to watch out for it. And there we go. The field between a pair of charged parallel plates is uniform and proportional to the charge on the plates, and varying the distance has no effect. Okay, we just saw that. Again, charged plates, just to be more clear here too, the charged parallel plates means no battery is connected, no battery remains connected, I should say. A battery might have been connected originally to build up a charge, but then it's removed. If there's a battery still connected, that's the one we're going to see later on. We're going to describe it as there's a voltage applied across the plates, and that's different. Okay, that's a different scenario, but we're not dealing with it yet. So far, the ideas, it's a lot. It's just ideas at this point, though, right? And so I want to be able to put a little bit of a math name to the face here, if you will. So we're going to look at electric field strength. Okay, this probably would normally separate into 2 lessons here. So we're going to try to get it because we're supposed to do 2 per day, right? So hold on to your hats here. If you need a body break once in a while, of course, stand up and do a couple jumping jacks, whatever. But here we go. So we quantitatively work with gravity strength in gravitational fields, like G equals 9.8 is familiar from gravity, right? So G is really like force per mass, if you think of the F equals mg equation, right? We're going to talk about electric field strength. We're going to talk about force per coulomb, newtons per coulomb. So as a concept, like if you know what electric field strength is as a concept, which is just how much force there is per coulomb, just like with gravity, how much force there is per kilogram, that's not a hard equation to remember, right? The weirdest thing is the symbol for it is this curly E. I don't even know the correct name for it. Curly E, okay? So curly E is electric field strength, newtons per coulomb, force per charge, right? Let's add that in, force per charge. Not force per charge. How did that happen? All right, so force per charge. And of course, Fe is the electric force that we calculated electric force in all sorts of examples yesterday in the homework. Q is, of course, electric charge, right? So field strength, how strong it is, how much force there is per charge. The next step is to combine a previously known equation, which we know that Fe is really KQQ over R squared, right? So this is where we get into, one of them is the electric field charge and the other one's the one that's feeling it. So I'll mention that in here. So we're just going to put that equation into the new one. So curly E, we're going to say here that Q is going to be the charge that's causing the field. Q2 is going to be the test charge. Okay, so we're going to basically say KQ Q2 over R squared. Sometimes we'll say KQ Q test for like test charge. Okay. So here we go, Fe over Q2, Q2 being the test charge, right? So we got KQ2 over R squared per Q2. This one here and this one here are the test charge. So this is the test charge. Test charge that is affected by Q's electric field. Right? Don't worry about this part here, the gravity part for now. So that mathematically obviously is going to cancel out, and we're left with the, to regain control here. Sometimes it takes two for some reason. Weird. Here we go. My mouse is working again. Yeah, so we get that curly E can be written as Fe per Q, force per charge, or it can be written as KQ over R squared. Okay. So a lot of that's the same, of course. Electric field intensity is still the same. Force per charge, I even wrote it in there in advance. And the K value and the Q and so on are all the same. But this is the Q that's creating the field, right? The Q2 was the test charge that was affected by the electric field.
Could you explain there how you got rid of the other Q?
Yeah, I would just show, in order to show that in more detail, I would show mathematically K, Q, Q2 over R squared. And then dividing by Q2 is the same as doing times 1 over Q2. And then if we really wanted to show it, it'd be like, oh, so we've got a K, Q, and a Q2. And in the bottom, we have an R squared and a Q2. And so Q2 divided by Q2 cancels out, just divides out to a 1. So I was trying to show there that it cancels out, but sometimes more is needed. So does that help?
Yeah, thanks.
Perfect. Undo that, lock that in place. That's already locked. I just need to move this up and out of the way a little bit. Q2 is back up like that. So I'm just going to point out that a little bit better here. Q2, right? That's that test charge that's being affected. It cancels out. Doesn't matter what charge you're talking about. We're talking about force per charge, right? So you put in the charge value and it determines that for you. But anyway, so in gravity, the same concept exists, right? It's like for the gravity, Fg equals mg. We're talking about a mass near Earth, let's say, that's experiencing a force, right? And so you'd have, in this case, m1 would be the mass of the Earth. M2 would be like U, for example, feeling a force of gravity. And so you could say G equals GM over R squared, and that's really what the 9.8 is, right? So we don't tend to talk about it this way as much as gravity. There's a couple different equivalent things we could say with gravity, but we don't bother. As gravity, it's just like always near Earth, right? So we're always dealing with Earth examples, and so it doesn't seem as necessary. But with charges, any charge is possible and at any time, and so you kind of get to need a little bit more of a way to think about it. Was there a question there? I heard a mic, but okay. So I will compare to gravity as a lot of times, but it's just weird that we don't really do that in the gravity. And it's also, of course, we're going to do gravity in a little bit more detail in this course, but I've changed the order, and so there's a couple snags along the way where it's like you'll see me saying just like it was in gravity, and you're like, but we didn't do that yet. But it doesn't matter, of course, because we're just doing what we're doing the charge stuff. Questions about this page? So you got this formula where electric field equals force per charge, and the equivalent equation is KQ over R squared. Okay. It is strange in the equation, that just acknowledge the strangeness of this, that the electric field, the force per charge, you don't actually need the charge you're talking about, because it's just the force per charge, right? So if it's 2, multiply by 2. If it's 3, multiply by 3. Like it's up here. You need the charge in this one. I should put, like, I feel like this should be Q here is the test charge, right? It's the test charge. So this idea here of the test charge that's being affected, this is still like QT or Q test or Q2 or whatever, however you want to word it in this page, force per test charge. Okay, just to have an equivalence between these two things. But yeah, so you don't actually need that value in this equation, which is kind of weird.
Moving on, so this is just, again, a little summary thing. So basically, if you're picturing gravity, you got a gravity force, you got an electric force. We know that gravitational fields, right? We know that fields cause gravity. Just have to regain control here with my mouse. So, what do we got here? So a force, force is caused by, I should say, by masses, right? Whereas in electricity or electrical fields, the force is caused by charges. That's the idea of the appropriate object in the field. The effect of the force is, of course, an attraction between masses, whereas with electric forces, electric fields, you can have an attraction or a repulsion. Field. So if you have a field, you test it by seeing if there's a force on a mass, right? Is there a force on it? Right? So you put a test mass somewhere and see if there's a force on it, and then in this one you'd put an imaginary positive test charge somewhere and see if there's a force on it. That's how you know if there's a field, right? See if there's a force on a charge. Field lines show the path a mass would go. It also shows the F net, right? F net. So in both cases here, the field line shows the net force, and that's important to have that definition or that reality that you can't have two field lines crossing, right? So it basically showing the path that a positive test charge would go. But of course, we know F net causes the acceleration, right? So the direction of the field line gives you the direction of the net force, which gives you the direction it'll go. Field strength vector, we can talk about 9.8 due to gravity, but that's specifically for Earth. They didn't have a capital there. I think we're supposed to. And then curly E, right? So it has always been kind of a curly G, I guess, but I don't know. Curly E, field strength. This is force per charge. Right? This one here, force per charge. In both cases, force per charge. The units of the field strength vector, we're talking about newtons per kilogram, whereas this one would be newtons per coulomb because it's per charge. Mathematical relationships, obviously, F equals mg. In this one, we had said this should be a curly E here. Just looking at it, I was like, what the heck are they doing? But that should be a curly E. We know curly E equals Fe per Q, right? And then here it's along the same lines as saying, like, G equal. It feels better to me to describe this one, to use that one, right? Whereas here we wouldn't normally have said, oh, gravitational field strength is how much force there is per mass. But with electricity, it's just our brain works different with it for some reason, right? This is the one that for sure to me is more obvious. Does this equation that I'm saying is obvious or like based on the concept that it's force per charge, does it solve to be this one? Of course it does, right? But you have to use a curly E there, not just an E. That's a mistake. I should fix that in the file in case I miss it next time. Important quantity symbols, of course, you've got like force due to gravity, you've got mass, you've got G, and of course in this one you got electric force, charge, and field strength vectors. Wow. So that's just a summary of things. And so this is one of those ones where it's like you just plug in numbers, right? If I give you the distance away from a charge and I give you the size of the charge that's causing things, then you can plug in, Notice that I can't use curly E equals Fe per Q because I don't have Fe and I don't have E and so on, right? So they're actually asking for this one. I was supposed to go green there. They're asking for this one. We don't know this one either. You can tell you don't have enough for that one. But in this one, we do have enough. You can tell you've got the K value, you've got the Q, and you've got the we want, sorry. This one, we got that one, we got that one. Because the K value is always known, right? So we plug in values and calculate. So curly E, just type in the numbers.
Okay. So then if you said a new question here, so if I don't know, 2 coulomb charge, I better do something smaller than that because it's supposed to be a small charge in comparison, right? So if I had a, what do I want to do here? A 1 times 10 to the negative 7 coulomb charge was at the 0.5 meter spot, location, whatever. What's the force? Well, then you could say, oh, curly E equals Fe per cube, right? So you could say, oh, so I've got my 1.1 times 10 to the 8 newtons per coulomb. I've got my electric force that results from the 1 times 10 to the negative 7 coulombs. And so this would lead to the actual value of the force. Okay, so you can sort of see how both equations are used by extending that question to do the other part of it. Once you know if you know the electric field, then you can figure out how much force there would be. So that is one you're going to want to refer to when you do the questions. We're talking about point charges, right? So I just thought I'd mention that if you rub your head on a balloon, that's not a point charge, that's a big sphere and so on, right? So we're going to talk about point charges just to simplify things, basically. And there was one more here. I just wanted to show the idea of this one. They talk about I don't know if they do the numbers for this one, I forget. Oh, this is the one with the numbers. This one's not though. The next one's not. So I'll just show this one here, just quick. They're talking about a charge that's suspended from a string, and it's balanced here. It's hanging from this string. This string is connected to like oops, not a star. Could be connected to a star, I suppose, but it's connected to like a ceiling or something like that. And it's balanced there. This is supposed to be vertical. They don't actually ask much in this question. If they did ask for like the tension in the string, you'd need to know the mass and the field strength and the charge and so on, right? But they did tell us that this is a 3.1 microcoulomb charge there, but they didn't tell us anything else. So they just actually asked what the charges at rest draw. Oh, they just wanted to just draw a free body diagram, I guess, right? So you would have just been asked to draw that and the idea here that the horizontal, they say it here, horizontal component of the tension force. So picture the horizontal component of this tension force, how it would be equal to this, which is very much like we tackled in recent questions. So I think that's a good little one just to sort of talk about. But so this one here, if you have 2 charges, and they're saying that these 2 charges, and they have the positive left of the negative charge, and so when you draw the diagram, you just draw it as they said, right? So you've got a positive charge and you've got a negative charge. They're 50 centimeters apart, and then they want to know the electric field at a point between them. Okay, so label point Y that's 10 centimeters away from the negative charge. Yeah, just follow those diagrams or this description, you get this diagram. No big deal, right? They want to know the electric field. The key part we have to pay attention to here is that this is a vector, right? And so curly E total is going to equal curly E, let's call it curly E from A, let's say, plus curly E from B. That's the idea, is you're going to have to add those things up vectorially. Okay, it's a force concept, right? So they're going to say, oh, the electric field intensity or electric field strength, that's interchangeable. Electric field intensity or electric field strength, so or just electric field. So i.e. Strength or intensity, which always equals the idea of newtons per coulomb. We're talking about curly E. Okay, so I'm also annoyed by their language. In people use very different languages, right, for this. But we're talking about electric field they're automatically looking for the strength or the intensity. In other words, we're talking about curly E. Okay, so in these questions, absolutely, one of the things is like, okay, what are they asking me? You got to be very, very careful about that. But end result, you know, calculating the force on a charge, I did that already on this question up here, right? The actual force, you just do the force times the field, or the charge times the field, I should say, right? So that's what that worked out to. Oh, they're doing, oh yeah, sorry, they're doing the, yeah, because you have the distance and you have the original charge. You don't have the actual charge. But you know that there would be a force of this much per coulomb. However many coulombs there are gives you the number, right? So at this stage, notice that this one right there, because we're talking about a positive test charge, would be to the right. So they say here, because the electric field's pointed away from positive charges, the field at that spot would be to the right. Then we also, of course, have to get the field due to this one, which would be an attraction. It would be to the right also, wouldn't it? Right? Because it's going to get attracted to that one, whereas this one was repelled from the green one. So we're going to get the number value, which is just a case of plugging in values. So great. The direction came from knowing that it's going to attract, you know, attract to the, right, that negative charge. So it ends up being to the right. The directions are by looking at the diagram. It's not the values of the things, okay? So this negative here actually means, remember, this negative actually means attract. And then you look at the diagram and interpret that that means the force is to the right. And that you gotta watch for that. That's kind of weird, okay? But then the net result is you add those up, they're both to the right, so they add up vectorially and give you a bigger number. So that is it with a minute to spare. But of course, you have to realize the curriculum mandated timing in Ontario still has another half an hour. So that is something to consider. That there is still a half an hour of you working if it's going to be the same as a regular semester where you're in class working hard on a grade 12 physics class. Okay, so to assist with that, if anybody is interested, I will log on to a Teams meeting at 1 o'clock. I will create a Teams meeting at 1 o'clock and I will be available for that extra half an hour for you. Okay, that's correct. Like the government says 75 minutes per period. 2 of them adds up to an extra half hours at this point. So I will be available at 1 o'clock. I will make a new meeting. And anybody who wants to join to get some help, by all means, okay? I'm available for that half an hour or more. I'm not gonna like hang up on you, okay? So extra help session scheduled officially 1 o'clock today and ongoing if it's well attended. I will log in, by the way, at 1 o'clock. I'm not hanging around for 10 minutes waiting to see if anybody's gonna show up. So if you're interested in getting some help at 1 o'clock, you might even already have that meeting going by the time I turn my computer on or like look at my computer at 1 o'clock, right? I'm not waiting around. It's like help sessions at lunch. When I used to do that, you know, I don't wait in 124 by myself for 10 minutes. People show up, I get help. If they don't, I leave. Okay. So I hope that's a good piece of news for you. There's an extra help session available and hope it gets you working on these things, you know, efficiently rather than waiting until you've forgotten some of it or whatever. But we are on overtime for now, and I'm hungry. You hungry? I'm hungry. Time to say goodbye, but I'll see you at 1 if you want to join me.
Thanks.
You're welcome.
Thank you. Have a good weekend.
You too. Thank you.